All right, I'm back from my short break. I'm going to be working on some of these concepts and stuff that I've identified. So basically, until until this end of this morning, what I'd been working on was getting through first pass of all the lectures and all the problem sets. So I've done that now. There's still a lot of conceptual work to be done, still a lot of things to be done. Now, I don't want to make it the case that, everything I've been doing up till now has been part of the learning process. So it's not fair to say, well, now the learning really begins, or now it really, because I'm doing this kind of stuff. Rather, it's sort of a question of having gone through all that, what was weak? What were things that I wasn't as good at that need to be worked on? So my sort of approach is always to try to triage, always to try to identify either the most important things, meaning that if you don't understand them really well, it's going to be really hard, or the things that you understand the weakest. So if you don't work on them, you're definitely going to get those things wrong in the class. So before, in this afternoon, the one immediately preceding to this, I had gone through all of my problem sets and I created this piece of paper here. Or basically, I just gone through everything. I wrote down questions that I wanted to work on, questions that I wanted to redo, stuff like that. And I also went through the problem sets and sort of wrote down concepts, facts, things that prevented me from getting those questions right. Now, I didn't include everything based on what I got wrong, because sometimes I got something wrong and then it's just obvious and you just know that now. Sometimes there's like a little trick to the problem, and then once you know it, you kind of know it. So there is stuff that I've here that I kind of mastered in the process of doing the problem. So I don't think it requires further work, but I did try to write down a bunch of things here that I thought were important. And then I spent some time reorganizing this. So I reorganized into two parts, some questions that I wanted to redo from the problem sets. So the ones that I've circled here are ones that I actually didn't do the first time around for whatever reason. Some of these early ones were because they required some materials I didn't have, and some of the later ones, I'm not sure what happened there or why I didn't do those, but I'm going to work on them again. And I did a kind of rough estimation of this. I think this is around 3 problem sets worth of work. I think it's going to take me around 3 days to get through all of this. Of course, if I don't get through everything here, it's, these are sort of an arbitrary choice. So this is not to say that everything needs to be done here perfectly. But I figured that given my pace I've been going at, that leaves about 3 days to work on that material. And I figured that in addition to writing the exam, which I'd like to do at the end of this time period, in addition to writing the exam, I also want to do a little bit of exam prep, meaning that I'd like to spend at least 2 days both writing the exam, if I'm going to write it in this time period, as well as doing some practice exams to get a feel for it. Now, as I mentioned, this has been a really challenging class for me, and I only have one final exam with a solution. So I have to make kind of a hard choice at the end of this project, because I'd hate to kind of waste my chance if I thought I was going to do a lot more studying. So at the end of this, if I feel like, you know what, I'm still a little shaky on this material and I'd like to get, like to really get it before I do the exam, then I might extend the project. I'm not saying I'm going to, but I might. I'm leaving that as a potential option. However, if I feel like, there's a reasonable chance that I can get through the exam, then I might do it this time. So what I'm going to do now is, if I consider that I have about 8 days left, if I don't do any weekend days, which I'm not thinking I'm going to do, but I mean, if I'm feeling it's really shaky by then, I might do it. So if I have 8 days, assuming I'm not doing the weekend, and I want 2 days, 1 day for pure prep and another day for maybe some prep plus writing the exams or final exam. I'm not sure whether I'm going to do all the exams or just the final exam. If I'm going to do that, then I'm looking at 2 days for that. That gives 6 days left. This one, I kind of roughly estimated it taking about 3 days. So that means that I don't want to spend more than 3 days doing this kind of stuff. Now, I'm kind of giving, this is sort of Feynman technique type stuff. I'm giving this a little bit of a shorter shrift, meaning I'm prioritizing it lower than doing more problem sets. And the reason why is just because I feel like the problem sets are the real meat of this class. I think the Feynman techniques is a more nice to have as opposed to a need to have. I mean, obviously doing the problem sets when I don't really understand something, I've been doing something kind of like the Feynman technique of going back and, you know, understanding things. I've done some already, but it's very easy to just do tons and tons and tons of these. So I could do these for days and days and days. And I think this is the stuff that, you know, because I have the opportunity for feedback. So what I'm going to do is for the rest of the day, I've got probably about an hour or so. I'm going to go and work through a little bit of stuff here. And then what I think I'm going to do is I'm just going to do alternating. So I think Friday, I'm going to work on this end of things. And then I'm going to do a day here, day here, day here, day here for maybe about 5 or 6 days until I get done all of that. And then once I get done this or feel like I'm close enough to being done this, that I want to move on to a new set of practice materials, then I'll start shifting over to exams. And I don't have feedback for a lot of the exams. I only have feedback for that one set, which doesn't even belong to this session. But I can use the sort of problem sets even without the feedback to get a sense of, like, do I know how to solve this? Or is it like, oh, this is crazy difficult, I have no idea how to solve this? So it still gives a bit of feedback on that. Ryan's intervention is saying, motivated me to go on a meditation retreat. Well, good luck. I hope you enjoy your meditation retreat. So with that in mind, what I'm going to do right now is I'm going to work on, I think it was lecture 14, where there was some stuff involving from minute 36 to 57. I think I made a note here that it was about the phase and how phasal information encodes important properties of the potential there. And that was also something that I was struggling with, understanding exactly how the phase relates to things. So I think I'm going to work on that first. And we'll see, that's 20 minutes, but it may take me longer if I go through it more slowly. And so let's just start there and just see where it takes us. And then if I have more time, I might work on some other things too. So let me just put this over here for right now. Get my, oh, here we go. Where is my, okay, there we go. So I don't really know what to put here at the top for the Feynman technique, but I think it's going to just be, I'm just going to call it a deep dive. Oh. All right, let's let me just open up the do I have that? I think maybe I need to make a new one. Oh, let me open up lecture 14.
The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare. Reorganizing the scattering in 1D.
Weird. Okay. All right. Let me just add. Oh. Let me just add some other elements here. And let me add this camera, and I will crop it here. And let's crop that. And let me just scale it down to here. think that's roughly what I have here. And then let me just adjust this one over a little bit. Maybe. It's hard to get everything to fit on these things. I might just leave this here and then keep my... I know you guys can't see what I'm doing because I haven't sent it to live yet, but I think this will be okay. I'm going to maybe make mine a little bit bigger just because otherwise... I think this will work. Let me see if I can. All right. Okay, let's try to roughly center this here. Oh, this is kind of ugly, but I think that this is probably the best way I can maximize the screen real estate here. And I want to go from 36. So let's just go a little bit before 36.
This is the reflected wave. I'm just going to call this R. Okay. And then on the right, we have e to the I cap.
Let me just pause and just reconsider where, just so I know exactly what's going on here. Lecture 14. Here, okay, so so this was involving a Gaussian movement, I think.
There's only a wave traveling to the right, and the coefficient is the transmission amplitude. So this is what we normally write. But then I'm using the function, the theta function, so-called theta function. Theta of x is defined as 0 when x is less than 0, and 1 when x is greater than 0. Okay, so this is a function 1. So this allows me, using theta function, allows me to write this thing as a single function without having to goose around with lots of terms. Is that cool?
Just take into account one sentence because otherwise we should have something.
Fantastic. Excellent. Excellent. Thank you so much. So here what I want to do is thank you. What I want to do is I want to think of the wave function. So this is a good description when the particle is far, far away. And this is a good description when the particle is not in the potential. So I want to just imagine this. Sorry, thank you. I totally glossed over this step. I want to imagine this as a potential where all of the matching is implemented at x equals 0. Okay. So when I write it in this fashion. But the better way to, another equivalent way to think about this is a good description of the wave function when we're not inside the well. So for the purposes of the rest of the analysis that I'm going to do, this is exactly what the form of the wave function is when we're not inside the well. Okay. And then let's just not use this to ask about questions inside the well. When I write it in this theta form, or for that matter, when I write it in this form, this is not the form. What I mean is left of the well and right of the well and inside.
So let me just recap where I'm at right now. So this is Okay, so I think I'm up to speed with where he is now. And then let's shift over.
T e to the ikx. Inside, it's doing something else.
So taking
But we don't want to ask questions about it. Okay. Cool. That's just going to simplify my life. Yeah.
Lowercase t then just the square root of capital T.
It's the square root of capital T, but you've got to be careful because there can be a phase. Remember, this is the amplitude, and what it really is this reflection is b over a, and these guys are complex numbers. And it's true that b over a norm squared is the transmission probability, but b over a has a phase, and that quantity I'm going to call t, and we'll interpret that in more detail in a few minutes. Okay. So it's of this form, and I just want to look at each of these three terms. And in particular, I want to focus on them at time 0. So at t equals 0, what does this look like? Well, that first term is integral dk of f of k e to the ikx.
So hold on a sec. So let's taking the Fourier of our combined fields. So I want to go back where he actually wrote out this formula here. Where did he write down the Fourier transform?
For the square well, in positive energy scattering states, the plane wave are the energy eigenstates states, which I will label by K, just because I'm going to call E is equal to h bar squared K squared upon 2m, which is the energy, the energy is a constant, which is the K asymptotically far away from the potential. The wave function I can write as 1 over root 2 pi times e to the I kx when we're on the left-hand side, but left is equal to multiplying by theta function of minus f, which is 0 when its argument is negative and positive when its argument is, 1 when its argument is positive. Plus, we have our reflected term, which has an amplitude r, which is the function of k. This is the reflection amplitude, so we're going to see on a e to the minus I kx. Again, on the left-hand side, theta minus x. Plus, the transmission amplitude, whose norm squared is transmission probability e to the I kx when we're on the right. X was theta. So this is just a slight differentiation of what we usually write with left and right separated. So what do we want to do now? If we want to decompose our wave function into the actual energy eigenstates. And so the way we're going to do that, and having done that, having expanded our wave function in this basis, we can determine this evolution following first we can do, but we expand the wave function at time 0 as an integral dk, and we pull the root to pi out. And we have some Fourier transform, which I'm not going to call f tilde because it's slightly different than the f we used before, but it's what the expansion coefficients have to be. F tilde of f tilde of k times this piece, phi sub k. 5k. Good. And let me actually write this out in terms of let me actually take this product and write it out in terms of the 3 terms. So those 3 terms are going to be f of k tilde e to the I x theta minus x plus f tilde r e to the minus I kx theta minus x plus f tilde t e to the I kx theta of x. So let's look at these terms. This wave function now. Oh, and, sorry. Finally, we want to look at the time evolution. But this we started out as a superposition of states with definite energy labeled by k. So we know the time evolution is e to the I kx minus omega t. E to the I minus I kx plus omega t. So minus I omega t and kx minus omega t. So we can immediately, from this time evolving wave function, identify these 2 terms as terms with a central peak moving to the right, and this a central peak moving to the left, kx plus omega t. Everyone cool with that? Questions? Okay. Yeah. How that? Sorry. Say again.
So I just did this part. So let's just go back. Where is he?
I think of the wave function. So this is a description when the I write it in this theta form, or for that matter, when I write it in this form, this is not the form when he is left of the well. It's not. It's just. Zero. What does this look like? Well, that first term is integral dk of f of k e to the I kx minus omega t. Okay, theta of minus x. Notice that theta of minus x is independent of k. It's independent of the k integral, so this is just a function times theta of minus x. And this function was constructed to give us the initial Gaussian.
So let me just write here. Okay.
So this is just, and this was at t equals 0. So this is just our Gaussian at position x naught, centered around value k naught at time equals 0. Theta of minus x. Okay. This is just saying that, at x, at position x, of x naught. So all this function is this is the Fourier transform of our Gaussian, and we're undoing the Fourier transform. So this is just giving us our Gaussian back. And as long as the particle is far away from the well, so here's the well, and here's our wave packet, the theta function is totally irrelevant because the Gaussian makes it 0 away from the center of the Gaussian anyway. And so, just as a quick question, if we look at this as a function of t, so we put back in the minus omega t. So if we put back in the time dependence, this is a wave that's moving to the right, and we need to make that, to be more precise about that. What does it mean to say it's a wave moving to the right? Well, this is an envelope on this set of plane waves, and the envelope, by construction, was well localized around position x, but it was also well localized in momentum. And in particular, the Fourier transform is well localized around momentum k naught.
So let me just write down that.
And so using the method of stationary phase, we're just asking where is the phase constant stationary. We get that the center of the peaks, the central peak of the wave function satisfies the equation ddk naught. If you're not familiar with stationary phase, let the recitation instructors know, and they will discuss it for you.
So this is a new concept. Let me just try to see. I want to jump over here. Okay, let's look at it, and then I'm going to make a note about stationary phase after, because this is what I was finding confusing, I think.
So the points of stationary phase of this this superposition of this wave packet lie at the position d.
So points of stationary
ddk naught of kx. Sorry, ddk of kx minus omega of kt evaluated at the peak k naught. Of the distribution. But ddk of kx minus omega t is for the first term x, and for the second term, ddk of omega. Well, we know that omega, we're in the free particle regime. Omega, where did it go? Well, we all know what it is. It's h bar k squared upon 2m. We take a derivative with respect to k. We get h bar k over m. The 2's cancel. So x minus h bar k over m.
Okay. So this is just this. And this is this. And why is that? Well, this is T?
T.
Yeah, T. Must have had energy. I think it was h bar squared. Yeah, I'm trying. I think it's because it's the energy. I think it's just the definition of the energy. Reed's helping me out here. He's saying that omega k, this should be equal to h bar k squared over m. I thought the energy operator was, because we have a phase. When we have the phase, the time evolution, we have e to the I e t over h bar. Oh, yeah. And our energy, okay, so that's why. All right. Where omega k is equal to h bar k squared over 2m? Yeah, 2m. Our energy E is h bar squared k squared to m. And evolution is e to the I. Okay.
And a place where this phase is zero, where the phase is stationary.
So taking what about here? So what is the physical meaning of this stationary phase? So because I don't remember learning what stationary phase meant, but I think we can just kind of guess at it from looking at this. So it is the derivative with respect to k. So this is how the phase changes based on the wave number. When Reed says, stationary phase is a math technique for approximating integrals. Okay. So what's the idea here? We're having you know what? I'm going to jump over and look this up. 1 second. Let me just shift over here. Let's go here. As much as Reed is helping me out here, I think I'm going to want to look this up. A more verbose description. Oh, this is Wiktionary. I want Wikipedia. All right. Stationary phase approximation is a basic principle. Applying the limit as k goes to infinity. The main idea of the stationary phase methods relies on cancellation of sinusoids with rapidly varying phase. If many sinusoids have the same phase and they are added together, they will add constructively, or if the same sinusoid phase which change rapidly as the frequency changes, they will add incoherently, varying between constructive and destructive addition at different times. So I guess the idea being that when we did our Fourier transform of our Gaussian, we should have something like this. And this is because at some kind of precise value, these are all going to add up, and everywhere else they're all going to cancel out. Is this what we're looking at here? So this is our I think the idea is that if we take the Fourier transform of a Gaussian, I think that is also Gaussian. I think that that also works that way. And if it's also a Gaussian, then it has some central peak. And this is where ddk is equal to 0 also corresponds central frequency. I'll just put central frequency or K. Because if we're looking in, yeah. So if our Fourier transform only has one maxima, because it doesn't really matter whether it has more than one maxima, but this would be like places where it's a maximum. So when dk of stuff there is a maximum or minimum contribution from the Fourier transform in sinusoids. Sinusoids? I think that's the explanation. Let's watch a little bit further.
Moves over time as x is equal to h bar k over m p. But h bar k over m, and that's the momentum. P over m, that's the classical velocity. So this is v naught p, the velocity associated with that momentum. So this is good. We've done the right job of setting.
Yeah, I'm not sure whether you can put links in the chat, Reed, unfortunately. YouTube might be blocking it just to prevent spam. So this is P, and then this is velocity. So this is kind of roughly how fast this wave packet's moving.
Up our wave packet, we built a Gaussian that was far away, that was moving in with a fixed velocity towards the barrier. And now we want to know what happens after it collides off the barrier. Cool? So what we really want to ask is, at late times, what does the wave function look like? Well, at late times, the position of this, so again, we're focusing on the first term, the position of this wave packet at late times of positive t is positive. And when it's positive, then this theta function kills its contribution to the overall wave function. Right? This theta is now theta minus a positive number, and this Gaussian is gone. What is it replaced by? Well, these two terms aren't necessarily zero. In particular, this one is moving to the left, so x is, as time goes forward, x is moving further and further to the left. And so this theta function starts turning on. And similarly, as x goes positive, this theta function starts turning on as well.
Yeah, Reed is suggesting Olga Smirnova stationary phase. I'll just copy that over. I'll just look at that real quick. Ooh, I think my thing is a little bit too wide. Yeah, I'm not sure what exactly to make of this image. You know what? I'm gonna just. I appreciate the help, Reed. I think I'm just gonna go forward with this because I think I have enough of the idea to understand what the point being made is. But I think there's definitely some stuff there.
Let's focus on this third term.
So let me just write down. There might be some stuff in 803 about this. So I might look for 803 stationary. Let me just do a quick check for 803 to see if there's any lectures about that. Oh, I'm doing 2 microphones here. Sorry about that, guys. Sometimes it adds another microphone when I'm adding the camera, unfortunately. Let me just do a quick look at... let me just look up. MIT 803. I think it's this one. Do we have a stationary phase? So we do have dispersive medium, so we do have that. No, I don't see stationary phase here. It might be in here, but it's at least not listed clearly. Okay, I'm just going to leave that.
So let's focus on this third term. So, in particular, that term looks like integral dk over 2i.
So hold on a sec.
F times the transmission amplitude times e to the I kx minus omega t. Okay. And there's an overall theta of x outside. But for late times, where the center of the wave packet for the transmitted wave packet should be positive, this theta is just going to be 1, so we can safely ignore it. It's just saying we're far off to the right. And now I want to do one last thing. This was an overall envelope. This t was our scattering amplitude, and I want to write it in the following form. I want to write it as root t e to the minus I phi, where phi is k. So what this is saying is that indeed, as was pointed out earlier, the norm squared of this coefficient t is the transmission probability. But it has a phase. And what I want to know is, what does this phase mean? What information is contained in this phase? And that's what we're about to find. So let's put that in. Here we have root t.
This is what? This is our phase. Wave number.
And minus phi. Okay, where omega and phi are both functions of k, because the transmission amplitudes depend on.
Oh yeah, t here is a different t than t for time. I wasn't making that mistake before, but I agree with you. It is a little bit bad notation here.
Okay. And now I again want to know, how does this wave packet move? If I look at this wave packet, how does it move en masse? How does, as a group of waves, how does this wave packet move? In particular, with what velocity? So I'll do, again, make an argument by stationary phase. I'll look at a point of phase equals 0 and ask how it moves over time. And the point of stationary phase is again given by dvk of the phase kx minus omega of kt minus 5k is equal to 0. Evaluated at k0, which is where our envelope is sharply peaked.
Okay.
So this
evaluated k0. What did I do here?
expression is equal to, this is again x minus d omega dk, that's the classical velocity, v naught t, minus d phi dk. But just as a note, d phi dk is equal to d omega.
Okay, so once again, leftward, rightward. I think we're doing, I've been doing split my left and right. Coming from left, leftward. This is rightward. That's leftward. I'm screwing up my leftward, rightward stuff. I don't think I wrote it down anywhere else. Okay. Moving right at V naught. Our group velocity Now a phase shift. So let's see here.
Dk. Define the omega.
So let's do this again. This is just simple chain rule here. d phi dk is equal to chain rule.
But this is equal to, this is just the chain rule, d omega dk, that's the classical velocity. D omega, or d phi d omega, that's d phi de times h bar. I just multiplied by h bar on the top. And
So h bar. How did we get this? R omega. Yeah, because then this was just with minus h bar. Okay. Calling that E is equal to omega h bar.
bottom. So this is equal to x minus v naught t plus h bar d phi de. So first off, let's just make sure that the units make sense. That's a length, that's a velocity, so this had better have units of time. Time, that's good. So h bar times d phase over de. Well, phase is dimensionless. Energy is units of energy. H is energy times time. So this dimensionally works out. So this is 0. So the claim is that the point of stationary phase has this derivative equal to 0. So setting this equal to 0 tells us that the peak of the wave function moves according to this equation. And so now, so this is really satisfying. This should be really satisfying for a couple of reasons. First off, it tells you that the peak of the transmitted wave packet, not...
So hold on a sec. Our original speed change speed because of the potential this makes sense classically because
not just a plane wave, the peak of the actual wave packet, well localized, moves with overall velocity v naught, the constant velocity that we started with. And that's good. If it was moving with some other velocity, we would have lost energy somehow. That would be not so sensible. So this wave packet is moving with an overall velocity v naught. However, it doesn't move it doesn't move along just as the original wave packet's peak had. It moves as if shifted in time. Okay.
Someone's asking me what's the idea behind recording these? So my idea for live streaming the project I've talked about a little bit is just that I wanted to kind of document the whole process of the project. So I don't expect most people to watch the whole thing, but I've done these kind of learning projects before. And I mean, this is not necessarily the most interesting one because I'm just doing a class. But one of the things that I found challenging is that after it was done, I was trying to show people what I did or trying to talk about it. And it was always challenging to kind of figure out what to say and what not to say. Whereas if I do it all live stream, there is a record of everything that I've done. So that's a big part of it, is just documenting it for me. And then also hopefully I have sort of, I have video of me doing various things so I can, if I want to talk about some particular moment, I already have recorded footage of it.
So the phase, in order to point the gradient of the phase with respect to energy, the rate of change with energy of the phase times h bar, is giving us a phase, a shift in the time of where the wave packet is. So what does that mean? So let's be precise about this. So let's interpret this. Here's the interpretation I want to give you. So in the absence, so consider classically the system. Classically, we have an object with some energy, and it comes along, it rolls along, and it finds a barrier or a potential well. And what happens when it gets into the potential well? It speeds up, right? It's got a lot more energy relative to the potential. So it goes much faster in here, and it gets to the other side and it slows down again. So if I had taken a particle with velocity, so let's call this position 0, let's say it gets to this wall at time 0.
This is not actually true. Hold on a sec. I think this is actually not true, what I just wrote. So
moving with x is equal to v naught t, if there had been no barrier there, then at subsequent times it would get out here in a time x, that distance over v naught, right? However, imagine this well was extraordinarily deep. If this well were extraordinarily deep, what would happen? Well, basically in here, its velocity is arbitrarily large, and it would just immediately jump across this well, yeah? So its velocity, so this would be a perfectly good description of the motion before it gets to the well, but after it leaves the well.
So what do we have here? We have this x is equal to v naught t H bar. Not change in speed, change in, let's say time saved, lost. So, yeah, I think I'm just going to watch him do it.
Position is going to be V naught T plus, well, what's the time shift? The time shift is the time that we didn't need to cross this gap. And how much would that time have been? That time would have been, well, it's the distance divided by the velocity, right? So that's the time we didn't need. So T plus, it moves as if it's at a later time, T plus L over V naught. Cool? So if we had a really deep well and we watch a particle move, we would watch it move x naught, x is V naught T, V naught T, V naught T, V naught T plus L over V, V naught T plus L over V, okay? So it's the time that we made up by being deep in the well. So there's a classical picture because it goes faster inside. So comparing these, here we've done a calculation of the time shift due to the quantum particle quantum mechanically transiting the potential well. Yeah. So let's compare these. The classical prediction, this says the classical prediction is the time it took, delta t, classical, is equal to L over V naught. And the question is this the same? So one way to phrase this question is this the same as h bar d phi dE evaluated at k naught? Okay. And from our results last time, for the amplitude c over a, we get that phi is equal to, which is just the minus the argument or the phase of c over a, or the transmission coefficient transmission altitude little t. Phi turns out to be equal to k2l minus arctan
so this is going to be
of k1 squared plus k2 squared over 2 k1 k2 tan of k2l. Okay, I look at this and it doesn't tell me all that much. It's a little bit bewildering. So let's unpack this. What we really want to know is this close to the classical result? Okay. So here's a quick way to check. We know this expression is going to simplify near resonance where the sign vanishes. So let's look, just for simplicity, near the resonance. And in particular, let's look near the resonance K2L is equal to n pi. Then it turns out that a quick calculation gives you that h bar d phi dE at this value of k, that value of the energy, goes as L over 2 V naught times 1 plus the energy over the depth of the well, V naught. Now remember, the classical approximation was L over V naught. We just did this very quickly. We did it assuming an arbitrarily deep well. So V naught is arbitrarily larger in magnitude than E, so this term is negligible. So where we should compare that very simple naive classical result is here, L over 2 V naught. And what we see is that the quantum mechanical result gives a time shift which is down by a factor of 2. Okay? So what's going on? Well, apparently the things slow down inside. The time that it took us to cross was greater than you would have naively guessed by making it arbitrarily we can make that a little more sharp by plotting as a function of E over V naught. The actual phase shift. So the classical prediction, if you do a better job than saying it's infinitely deep, the classical prediction looks something like this. Okay. And this is for delta t, the time shift, classical. When you look at the correct quantum mechanical result, here's what you find. Oops. Where the difference is a factor of 2, 1/2 a height down, and again, 1/2 a height down. So this is that factor of 2 down.
So it doesn't slow down in the well, it just only
stairs. So the wave packet goes actually a little bit faster than the classical prediction would guess, except near resonance. And these are at the resonant values of the momentum. At the resonant values of the momentum, it takes much longer to get across. Instead of going a little bit faster than the classical result, it goes a factor of 2 slower than the classical result. And so now I ask you the question, why is it going more slowly? Why does it spend so much more time inside the well, quantum mechanically, than it would have classically? Why is the particle effectively taking so much longer to transit the well near resonance?
Classical particle's not going to do that.
Yeah, exactly. So the classical particle just goes across. The quantum mechanical particle has a superposition of contributions to its amplitude where it transits, transit, bounce, bounce, transit, transit, bounce, 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 transit. And now you can ask, how much time was spent by each of those imaginary particles imaginarily moving across? And if you're careful about how you set up that question, you can recover this factor of 2, which is kind of beautiful. But the important thing here is when you're hitting resonance, the multiple scattering processes are important. They're not canceling out. They're not at random phase. They're not interfering destructively with each other. They're interfering constructively. And you get perfect transmission precisely because of the constructive interference of an infinite number of contributions to the quantum mechanical amplitude. Okay, and this is, again, we're seeing the same thing in this annoying slowdown. And this tells us another thing, though, which is that the phase, the scattering phase, the phase in the transmission amplitude, contains an awful lot of the physics of the system. It's telling us about how long it takes for the wave packet to transit across the potential effectively. Yeah. Sorry, the vertical axis here is the time that it takes, the shift in the time due to the fact that it went across this well, went a little bit faster inside. Okay, so empirically what it means is when you get out very far away and you watch the velocity, the motion of the wave packet, and you ask, how long has it been since it got to the barrier in the first place? It took less time than you would have guessed by knowing that its velocity is v naught. And the amount of time less is this much time. That answer your question? Good. Yeah?
Approximation the amplitudes of 1/2. Why is the first one it bounces around twice?
So the classical amplitude is, so when we compare the classical amplitude, the limit that v naught goes to infinity, so the comparison is just a factor of 2. Okay, it's more complicated out here, as I guess it's in the limit that v naught is large. This is exactly 1/2. Well, the resonances are leading to this extra factor of 1/2. And so as you, I have to say, I don't remember exactly whether as you include the subleading terms of 1 over v naught, whether it stays 1/2 or whether it doesn't.
So I think that's what I was wanting to look at for this one here. I think I'm probably just going to leave it at that for today. I don't think I'm going to jump into anything new, but I just did a little bit of this just because I was not sure quite what to do. You know, do I want to put my I'll go like this. Yeah, so I'll just sort of address some of the things people are saying in the chat. I'm getting a little bit better at managing chat and studying at the same time. I wasn't quite sure how that was going to work when I was doing the live streaming. Someone asked why I'm doing this live stream. Well, obviously I'm aware that no one's going to watch me study for, you know, how many ever hours this is taking me to do. The reason I was doing this is one of the things I wanted to kind of do this during the MIT Challenge, to be honest. I thought my original idea was going to do weekly update videos and talk about the things that I learned. And so I would have loved to have done this for the MIT Challenge. Unfortunately, live streaming, that technology wasn't really around at that time, so it just never occurred to me to do something like that. And I wanted to do this. I wanted to talk about what I was learning, kind of just share in sort of the ideas and insights, and I could talk about it. Unfortunately, I quickly realized that that wasn't going to work because I would cover a whole class, which was usually 30 hours worth of fairly succinct lectures by people who know how to explain things in a clear and succinct way. 30 hours, and I was doing that every week. So if I was going to do an update video that's going to be 5 minutes, there's basically nothing I could explain from the class that I could even possibly even get started to do justice to the ideas. So I ended up switching to just giving these very high-level overviews of what I was doing, and then that evolved into, you know, giving various studying advice. Whereas what I wanted to do here is just, yeah, it is a lot of video. I don't expect most people to watch it, but the video exists, so if I want to edit it down into something more bite-sized or condensable later, I always have that opportunity. And also just because I know from watching other people that often the things that I think are important aren't going to be the things that you think are important about learning how someone does something. So one of these guys, I've taken drawing and painting classes from him before. He basically just does him doing the whole piece from start to finish. And I find that very valuable because very often the thing that he's talking about is not necessarily what I find interesting about that. Like, oh, I wouldn't have done it that way. You did it this way. Now, I don't want to say that necessarily, you know, you should do exactly what I'm doing. But a lot of people have asked me questions about how I study for something like this. So I thought, you know, this is a good way of doing it, just showing me how I'm doing it, what's my thought process. I've tried to reflect as much as possible, like verbalize things. I'm not normally talking when I'm studying, but I've been trying to verbalize things so you can kind of get a sense of how I'm thinking about handling this kind of problem. And I'm not saying I'm always doing the right thing. I think learning is particularly challenging this way because once you know how it works, you kind of know what you should have done. And so always when you're learning things, there's a little bit of, you kind of are working with not the full pieces of the puzzle. So I've tried to talk about it in a general way. And so I'm hoping that all these live streams, I can kind of piece them together later. It's definitely helpful for things like, what does it actually look like to do the Feynman technique? Why am I doing it? What's motivating it? What, you know, I did the start of this afternoon, I did a whole discussion of like my whole theory of how, you know, how you should think about problem sets and coverage and things like that. And so it's not always going to be, necessarily that interesting. I know there's probably just hours of me watching lectures. Well, you can just watch those lectures yourself. But I'm hoping that as a record, you know, this will be helpful to people later. Now, it was a little unfortunate that I chose this project exactly how I did because the class has been harder than I thought it was going to be. Not impossibly so, like I have been making progress, but I think if knowing what I know now, I probably would have reformulated the project to either do 803 privately first so that I could get a little bit more up to speed on that, or I would have done 804, 805, 806, or 803 maybe to 806 as just a bigger project, just because then I would have not had as much time fumbling around. So yeah, this has been kind of an interesting project to work on. I'm nearing the end now. It's now just sort of a process of filling in the weak points, doing as much remaining practice as I can, and I'll just sort of see how it turns out. Obviously, I'm not going to reach a level of perfection in this month. I think there's still more work to be done. So if this was me in an actual class, I mean, this would be a class that would be very hard if I had to do them, you know, in these actual time constraints, definitely with these problem sets. But I think I've kind of also shown how you can learn a class like this on your own. And this is definitely a hard class for me. So maybe this class is too hard for you if you've not taken it, obviously any of the prerequisites, or if you're not ready for it. But I'm hoping that you can analogize to that, create an analogy to that of how you might tackle a class that's very hard, learning on your own, where you can't ask people questions and you have to figure out things for yourself and that kind of thing. So this has been kind of an interesting process. I've definitely had fun doing it, although definitely been needing to put in more time than I thought I was going to need. Tomorrow morning, I'm going to try to be back early again, try to do as much as I can in the day. I think tomorrow is going to be all Feynman technique, maybe make some formula sheets with some common like identities and processes that I can do some active recall with. And then, I might do a little bit of practice on some skill things. Honestly, the problem sets have just been pretty voluminous practice. So I don't really feel like I need to do too much drills beyond that. Maybe dimensional analysis, but beyond that, I think, this has been pretty good. And so I'm going to work on Feynman techniques tomorrow. And then I think I'm going to just do alternating days of practice Feynman techniques, or I might do mornings, afternoons, alternating, of switching up the techniques for the remaining, because I wanted to put about 6 days more of study, and then it's going to be focusing on the exam itself and what I want to accomplish for that. I do think there's going to be stuff I want to do past this. I had this idea of creating a kind of non-mathematical video summarizing the kind of intuition I've gained about these things. I've been thinking about how I want to do that. I don't think I'm going to be able to work on it in the time period, but I might finish this, let it kind of incubate for a little while, and then in the next month or so try to come up with either an article or video. I was thinking video at first, but then I'm leaning now towards article, just because if I find out that I've made mistakes or something, it's a lot easier to edit than a video. And definitely at this level, it's certainly possible that I'm going to make mistakes in intuition. You can see I've had to cross this out because I thought I had an intuition and I'm like, oh, no, that's actually not true. So sometimes that happens still. And I think the only way to get that really perfect intuition is just to spend a lot more time with it, which I don't know when I'm going to have time to do it, but I would definitely like to take 805 and 806. This has been a really good start, but I feel like it's just whetted the appetite rather than really feel like I've been satiated with quantum mechanics. So I think I'd like to try 805 and 806. I don't think I'm going to do another ultra learning project that's a month long like this immediately. I might do kind of what I was doing before, where I just watch the lectures just to get a kind of overall sense of it and just do that casually, and then decide whether I want to do deeper studying or kind of ultra learning later. One advantage of having done it this way, I will say, is that now that I'm kind of up to speed a little bit in the math here, it's going to make watching 805 lectures or 806 lectures a lot easier, because it's not going to be like, well, I didn't really ever practice that math, so I don't really know what they're doing or how they're deriving that. So you can kind of go a little bit further ahead in lectures to kind of understand at a high level, but you go too far and you're missing the kind of conceptual things. So they're just kind of doing a bunch of stuff. Well, obviously this means this and this means that, and it's all going over your head. So this has been a fun process. I'm going to be back tomorrow morning, and I will just keep working at it and doing Feynman techniques and working through some of these weak points in understanding. And I hope to see you there.